This is a class on the Lanczos iteration, or the Lanczos algorithm, which is a different way to compute largest eigenvalues and eigenvectors of very large symmetric matrices. So again, as we've talked about before, the problem is the following. Given a symmetric matrix, we want to find its eigenvalues and eigenvectors. And in particular, one thing we might care about, as we've seen in many different applications, is we want to find its top and bottom eigenvalues and eigenvectors very quickly. So we'd like to be able to find everything, but in particular, we'd like to be able to find those. So we've talked about other algorithms like the power iteration and so on, but now we're going to talk about the Lanczos iteration. So first, we need to discuss a few preliminaries that we'll be using throughout this lecture. So first is the notion of the Rayleigh quotient. So this is something that we've already discussed. So this is essentially the notion of the approximate eigenvalue of a vector x, where x is not an eigenvector, and it's defined as R of x is equal to x transpose ax divided by x transpose x. And as we discussed last time, there's an optimization-based explanation for where that comes from. Second thing that is of fundamental importance in the understanding Lanczos is something called Krylov subspaces. And the definition is as follows. So if we're given a vector Q and Rn and our symmetric matrix A, it turns out that what's important is we care about the span of Q, AQ, A squared Q, and so on. And it's so important that this is given a name, the Krylov subspace. So let's define the Krylov subspaces as script K of A, Q, and then little k. Let's define this to be the subspace that's equal to the span of Q, AQ, all the way up to A to the K minus 1 Q. And let's also define the Krylov matrix K. So notice that this is not script of A, Q, K. Let's define this to be the matrix whose columns are Q, AQ, all the way up to A to the K minus 1 Q. So clearly, the range of the Krylov matrix is the Krylov subspace. So one thing that we're going to be particularly interested in is finding orthonormal bases for these Krylov subspaces, and we'll see exactly why it is that we care about that. The next thing that we need in terms of background is a little bit about tridiagonal matrices. And one important fact is that if A is a symmetric matrix, then I can find an orthogonal matrix Q so that Q transpose AQ is equal to a tridiagonal matrix. Now, this is obviously true. If you know the spectral theorem, you know that if A is symmetric, we can diagonalize it. A diagonal matrix is obviously tridiagonal. But the point is that it's easier to find tridiagonal matrices than to diagonalize A. In fact, diagonalizing A is equivalent to finding its eigenvalues and eigenvectors. So the point is that tridiagonalization is often an intermediate step to diagonalization. And recall that if Q transpose AQ is equal to a diagonal matrix, then we've basically found its eigenvectors and its eigenvalues, because eigenvectors of A are just the columns of Q, and eigenvalues of A are lambda 1 to lambda n. So let me make a star here and say that this is extremely important. So so you should be comfortable with facts A and B. So please make sure you are comfortable with A and B. So some facts about tridiagonal matrices are that they are much more easy to find eigenvectors and eigenvalues. So this is why this tridiagonalization is often an intermediate step, and we'll see that this is exactly what happens in the Lanczos iteration. This is what happens in the Lanczos iteration. Okay, so it also, now going back to the previous point, it turns out that there is an important connection to these Krylov subspaces that we just introduced. And it says the connection is as follows. So let's suppose that Q K, which by that I'll denote Q1 to QK. So the matrix whose columns are Q1 through QK. Maybe it helps if I write it like this, so to make it clear that this is a matrix and these are columns. So suppose that this is an orthonormal basis for the Krylov subspace of level K. So clearly Q1 is an orthonormal basis for the Krylov subspace of level 1, because that only contains the span of Q1. So we're saying that the following is true for all K from 1 up to n. So then this will give us a little practice with thinking about Krylov subspaces. Then the claim is that Q transpose AQ is tridiagonal. So this isn't too difficult. So let's prove this. Let's prove this claim. So let's look at what element Tij is. So what is this? Well, you should show, or at least convince yourself, that this is exactly equal to Qi, where again Qi is the ith element of Q. Oh, and when I write Q here, what I really mean is Qn, so the n by n matrix. It's really equal to Qi transpose A times Qj. And I want to show that this is equal to 0 for I bigger than j plus 1. So let's see why that's true. Well, we know that A Qj is in the span of Q1 all the way up to Qj, Qj plus 1, exactly because of the Krylov property. But moreover, we know that if by orthogonality of the Qj's, And because by orthogonality, this has to be perpendicular to qi if I is bigger than j plus 1. So therefore, the result follows. We also have a symmetry argument in there. Symmetry is used. Okay, so these are the basics that we need. So now we can go on to discuss what the Lanczos algorithm does. So here we give the key ideas and outline of the development and proof for the Lanczos iteration. So there's 4 key ideas, and they're all quite straightforward. So first, let's recall the definition of the minimum and the maximum eigenvalue. So so these are defined as follows. So the maximum eigenvalue, which I'll call lambda 1, this is equal to the maximum over all y different from 0 of y transpose ay divided by y transpose y. And similarly, lambda n, the smallest eigenvalue, is the minimum over all y different from 0 of y transpose ay divided by y transpose y. So notice that this max and this min is over all of Rn. Right? So in both of these, the max min is over all of Rn. So what we'd like to do is we want to find and then augment iteratively a k-dimensional subspace vk, k to index the dimension, so that if I were to define capital Mk to equal the max over all y, not all y in Rn, but all y in Rk of y transpose ay divided by y transpose y, and little mk to be the min over all y in vk of y transpose ay divided by y transpose y, these will be good approximations to lambda 1, lambda n, respectively. So this is the basis of the idea for Lanczos. We want to find subspaces and iteratively augment them. The second idea relates to Krylov. So we will show that an excellent choice for Vk is indeed the Krylov subspace at level k. So it's indeed what we denoted previously by this, where q1 is some initialization vector. Remember that even for the power method, we needed to find some initialization vector. So the third idea is as follows. Suppose that we found our Krylov subspace, and moreover suppose that qk, which is the matrix as before with columns q1 to qk, is an orthonormal basis for the kth Krylov subspace. So now let's write down what capital Mk or little mk are. Well, let's just choose capital Mk. Then by definition, if we write down what it means to be in, well, let me just write this out. So this is equal to the max over y in the Krylov space. I'll suppress the rest of the notation, but it's a Krylov subspace of dimension k. So what this means, y transpose ay this is exactly equal to the max over all y different from 0 of qk y transpose a qk y divided by qk y transpose qk y. So why is this true? This is true because by definition the range of qk is equal to the Krylov subspace, and so that's exactly what we're doing. So what we're going to show in this lecture is that in this case mk is close to the largest singular value, and largest eigenvalue, and little mk is close to the smallest singular, smallest eigenvalue. So the final point is to ask, how does this help computationally? So this is the final point we made in our preliminary remarks, which is that if Q is an orthonormal basis for the Krylov subspace, then let's look at the numerator of MK, of our expression for MK. We've got QK y transpose A QK y, which is just equal to y transpose QK transpose A QK times y. And what we saw is that this is tridiagonal. So this is some tridiagonal matrix, or as we'll see, it approaches it's tridiagonal when k is equal to n. So what we have for k is equal to n, what we have is Q transpose AQ, which is T, which is going to be some tridiagonal. Now we know that these have the same eigenvalues and eigenvectors, and moreover we know that it's easy to compute the eigenvalues and eigenvectors of a tridiagonal matrix. So this is if we wait all the way for Q equals to n. But the idea is that even for let me write this out. So for k is equal to n, eigenvalues and eigenvectors of A are given by the eigenvalues and eigenvectors of T. But for k less than n, turns out that it's very close. And we'll make this precise and see exactly what this means. But these 4 points spell out the basic ideas in the development and also in the proof techniques for showing what the Lanczos iteration does and why we choose to do that. So I've rewritten the problem here so we can keep it in mind, and I've added two new elements, or rather I've emphasized 2 new elements. The first is on sparsity, and we'll see why that is. So Lanczos, while it works for even non-sparse, it works particularly well for sparse matrices. And the second element is that I want to focus on being able to quickly find the top and bottom eigenvalues. So I don't actually want to have to diagonalize all of A. Is there a way to very quickly find, if you just care about the top and the bottom eigenvalues, can you exploit that fact that you don't want everything? Okay, so let's get into it and get into this first idea of how we augment the right subspaces. So let me remind you from just a few pages ago what we defined as the Rayleigh quotient. So this is R of x is equal to x transpose AX divided by x transpose x, and of course only defined when x is non-zero. So as an exercise, please show that R of x is always less than greater than the smallest eigenvalue and less than the biggest eigenvalue. Now let's define capital MK and little mk, but instead of using a subspace, let's look at orthonormal vectors that span that subspace. So for any collection, any sequence of orthonormal vectors q1 to qn in Rn, so this is an orthonormal basis, let's let qk to be that matrix which just has the first k. So this is an n by k matrix. And therefore, let's define exactly as we did on the previous page, capital MK to be the largest eigenvalue of qk transpose a qk, which is equal to the max over all y not equal to 0, y transpose qk a qk y divided by y transpose y, which we can just write as equivalently the max over all y with a unit Euclidean norm r of qk y. Okay, so note by the exercise above that this is actually going to be less than the top eigenvalue of y. You can even see now why this exercise is so immediate. And similarly, little mk is going to be equal to now the min. I'm skipping all the steps that I just wrote for the max, but they're identical. However, y with unit Euclidean norm r of qk of y. And for similar reasons, this is going to be greater than the smallest eigenvalue. So the idea is to design expanding subspaces, or now in terms of the orthonormal bases, we want to design and build, and in particular build in an iterative fashion our sequence of orthonormal vectors q1, q2, etc., so that mk and little mk are increasingly good estimates of lambda 1 and lambda n respectively. Okay, so let's see how we can do this and what should be a good, if I want to add, if I have q1 all the way up to qk, then what should be my qk plus 1 in order to improve both mk and little mk. So this is the challenge. So here are two optimization problems defining capital MK and little mk. So it's fairly easy to see that because R is a continuous function and because I'm maximizing and minimizing over a compact set, that the max and the min are attained. So let's suppose that the maximizer here, let's call that y upper bar, and let's call the minimizer for the lowercase y lower bar. There probably should be a k in there, but I'm suppressing it for now. So so therefore, let's denote uk equal to qk y upper bar. In other words, that means that r of uk is r of qk times y upper bar, and that's by definition of y upper bar, that's equal to mk, and similarly vk is qk times y lower bar, and therefore r of vk is equal to r of qk y lower bar, and that's going to be my little mk. So note that essentially by definition uk and vk are both in the span of q1 to qk. So now I'd like to add qk plus 1 so that the uk plus 1 and the vk plus 1 that I find in some way in the span of q1 all the way up to qk plus 1, this is the new element, are both improved. So the question is how we're going to do that. So how to choose qk plus 1. An optimization based idea would be to add qk plus 1 so that I could do a gradient step for improving mk or little mk. So in other words, so that the gradient of r at uk and that the gradient of r at vk are both contained in q1 up to qk plus 1 now that we've added this new element. I'm not saying this is optimal, but this is certainly a well-motivated idea. The question is, how can we add only one element in order to make sure that we're incorporating both of those gradients? So it turns out that we can do this. So let's see what these gradients are. So recall again that r of x is equal to x transpose ax over x transpose x. So now we can compute the gradients. So the gradient of this continuous function is just by simple calculation equal to 2 divided by x transpose x times ax minus r of x times x. So note in particular that this means that delta r of x for any x is in the span of x and ax. So let's survey what we've just discovered. So we found that uk and vk are both in the span of q1 to qk. That's by definition. And we know that the gradient of r at any point x is in the span of x and ax. That means that the gradient of r at uk is in the span of q1 to qk and a of q1 all the way up to a of qk, and so is the gradient of r of vk. So the key idea now is that we see immediately is Krylov. Suppose that that the span of q1 to qk is equal to the span of q1 aq1 all the way up to a to the k minus 1 q1. In other words, suppose that q1 to qk is an orthonormal basis for the Krylov subspace of level k. If that's true, then this tells us that the gradient of this tells us that uk and vk are in the span, I'm just copying from above, of q1 to qk, which is equal to, because it's Krylov, the span of Q1, AQ1, all the way up to a to the k minus 1 of Q1. And therefore, the gradient of UK, the gradient of R at UK, and the gradient of R at VK is going to be in the span of Q1, AQ1, A to the k minus 1 Q1, A to the k Q1. So that means we want to choose QK plus 1 so that we continue to have this Krylov property, so that Q1 to QK plus 1 is an orthonormal basis for the Krylov subspace. And that is one of the key ideas. That's one of the key ideas here. So, so basically, we've reduced the problem to finding an orthonormal basis for the Krylov subspaces. And not surprisingly, the key idea for the algorithm relates to tridiagonalization.